The lectures this week, and I'll be saying this on all three of these, are walkthroughs of how to use the computer program SPSS to do a lot of what we've been talking about for the last 3 to 4 weeks in class. I would strongly suggest that you actually download these and save them somewhere, not only for the purposes of having quick and easy access when you're doing the homework in this class, but they may also be very useful in other classes as well. So this walkthrough is specifically looking at how to run and interpret correlations and regressions using the statistical package SPSS. So if we're looking at a bivariate correlation, and bivariate simply means that we're looking at a correlation between two variables, the first thing we need to do before we even go to SPSS is make sure that it's appropriate data for this analysis. So a correlation needs continuous data. So again, we kind of talked about the different types of data, but continuous means that there are numerical values and that there are only numerical values. In other words, we have basically transformed whatever the questionnaire or whatever the response options were into a numerical pattern. Those numbers have approximately equal distance and they're sequential. So a 1 to 5 scale, a 1 to 9 scale, a 0 to 100 scale, it really doesn't matter, but it does need to be numerical. If your data is continuous, but it's on an A, B, C, D, E scale, you may need to convert it first, and we'll be talking about how to convert numbers in another one of these slides. So if you do indeed have a bivariate correlation, you have two variables, each variable representing a continuous data set, and you're waiting to see if they're correlated. We might be doing this for, like, for example, scores on an anxiety test versus scores on a depression test. It might be an odds or even test. We've divided the data into the scores that people had on the odd items versus the scores they had on the even items. It may be looking at time 1 versus time 2 of the same test. All of those are examples that we would be wanting to run a correlation and get an R to determine how well it was correlated. We can also be using correlations to determine if two things are not related. So for example, if I wanted to show that there was not a relationship between my measure of anxiety and, let's say, a measure of cognitive ability, then I would be looking at a bivariate correlation as well. So we're going to go to the analyze function at the top of SPSS once we have the data set open. We're going to scroll down to correlation or correlate, and we're going to select bivariate. Bivariate simply means two variables. That's going to open up the correlation screen. We're going to choose our variables in the left-hand column. We're going to click on them and we're going to bring them over. And again, we're doing a bivariate correlation. We're going to bring two variables over. It should be noted that we can bring multiple variables over. It will simply look at the correlations between all of those variables. Again, it's never going to look at the correlation between all three variables at once, but if we have three variables in there, it'll look at the variable 1 against variable 2 and variable 3. It'll look at variable 2 versus variable 1 and variable 3, and it'll look at variable 3 against variable 1 and variable 2. Again, the bivariate doesn't necessarily mean we only need two variables, though we do and need at least two. We can have multiples. What it refers to is that it's only going to run correlations between sets or sets of two variables. Once we've selected our two variables, we're going to make sure that Pearson is selected towards the bottom. That should be the default. That basically means we're running a Pearson correlation. And we also probably may want to choose whether it's a two-tailed or one-tailed test. We're not going to get into that much, but if you're in a statistical class elsewhere, you may actually be wanting to select whether you have a one or two-tailed test. In this case, we're simply looking for any differences. And the one-tailed versus two-tailed test basically tells the statistical package, are we looking for a directional relationship or are we simply looking for a relationship? In other words, if you know you're expecting a positive relationship, you might select a one-tailed test. If you really just want to make sure there's a relationship in any form, positive or negative, you're going to choose the two-tailed test. For our purposes, we're going to stick with the two-tailed test, and again, that should be the default function. And we're going to make sure that that flag significance is also clicked as well. Once we've done that and we have our two variables brought over, and again, how we're bringing these variables over is we're clicking on the screen to the left to find those two variables. Each time we're going to click that arrow to bring them over. And once we have two variables in the box to the right, we're going to click continue. We're going to click options. Options is simply going to bring up this small little menu here. Again, we're wanting to actually click means and standard deviations. This is basically just going to calculate the descriptive statistics for us as well. And we're going to hit continue. That's going to take us back to that correlation screen that we've already completed. And at this point, we're going to click OK. That's going to actually run the correlation for us, and we're going to get a results file. This file can be saved separately if you want, but here's what we're looking for. So since we click descriptive statistics, we're going to get the descriptive statistics. In this case, I chose two variables. One was simply someone's age versus the actual measure. And notice that I named the measure here alpha 0.96. That represents the fact that I was making a note to myself what the internal consistency or reliability of that test was, and that is 0.96. So it's a highly correlated test. It's a highly consistent test. The test itself, if I remember right, actually was a measure of sexism. So I'm looking to see, is there a relationship between age and sexism in this particular example? I've got my means, my standard deviations, and the number of people that were in the sample of each case. Notice that there was 77 people that provided age, 80 people that provided the actual data, which means that there were 3 people that actually completed the survey and did not provide their age. This statistical test is only going to be looking actually at the relationship between those that provided both variables. Next, we're going to actually take a look and see what the results are. So again, you're going to see this correlation table. And in this case, we're simply correlating 2 variables. But if we are correlating 3, 4, or 5, this would be a more complex table, but it would be providing us with the same information. We simply want to look at one of the boxes, which has age and alpha represented. It'll give us the correlation, it'll give us the significance, and it will give us the degrees of freedom. And again, for degrees of freedom in this case, for this particular test, it's n-2. However, it should be noted that you'll learn more about degrees of freedom in other statistics classes. At this point, I think degrees of freedom can be basically just summed down to it's an estimate of how many people were in the sample, and it always tends to be slightly less than the number of people we have in the sample. It's basically, again, an adjustment to make sure that we are feeling confident in the results. So in this case, we have an R of 0.068, or rounded up 0.07, so not a very strong relationship. Again, if we wanted to find the actual percentage of variance, we would multiply those two numbers together, 0.07 times 0.07, which would be even a smaller number. We have P, or how significant it is. Again, we generally want to see a low value here. What we're generally looking for in the social sciences is a significance of 0.05 or less. In this case, it's 0.554, rounded to 0.55. There's a 55% chance that the relationship we found is just purely due to error and random chance. So we would not report this as a significant correlation. Now, if we were trying to show that our particular measure was not related to age, that's actually good results. It tells us it isn't. It isn't following, we weren't expecting the relationship and we didn't find it. And finally, we have that N, which in this case is our degrees of freedom. So if I was going to report this, my degrees of freedom is n-2, so 77 people total were actually looked at in this correlation. Again, remember there were 77 people that provided age, 80 people that actually provided scores on the assessment, but 3 of them did not give age. So the assessment, or the correlation, the statistic, only looked at the 77 that we had scores for both. Our degrees of freedom is n-2, which means 75. So if I was going to report this, I would report it as shown at the bottom. A italicized R, all test statistics are italicized, parentheses, the degrees of freedom, so 77 minus 2, which is 75, what the actual value is, which is the R, which equals 0.068, what the P value is, 0.554, and again, we might calculate R squared. I would generally say we're not going to calculate R squared if we don't have a significant result, but if we really wanted to just illustrate how little of a relationship there was, we might do that. It's less than 1% of variance explained. Notice again, the R squared and the P are also italicized. So this is the APA way to present the statistical information. We would basically say we looked at a relationship between age and a measure of sexism, and that there was not a significant relationship, comma, and we then put in this information. R 75 equals 0.068, P of 0.55, R squared of 0.005. If we're doing a regression, now we are not being, we haven't really talked about regressions yet in this class. Regressions are basically the same thing as correlations, but they also allow prediction. And the simple regression is similar to a correlation. In fact, we're going to get basically the same information. If I looked at that same data, age versus sexism, and used a simple regression instead of a correlation and didn't add anything else, I'd find the same results. I'd find the same significance, though we're going to get a little bit of different information because we're also getting information about prediction. The reason I'm going to go over this is primarily just so you have access to a quick guide of how to do regressions in SPSS. Also, where correlations always look at bivariate relationships, we refer to this as a simple regression because we're simply looking at two variables. Regressions do allow us to look at multiple complex relationships. So if I put 3, 4, or 5 variables into a regression, I wouldn't get a correlation matrix just looking at the bivariate relationships or correlations between each two variables. I would actually get a statistical analysis of the entire relationship between those variables. So again, I'm going to click on Analyze once I have my data set open. I'm going to select Regression, and I'm going to go with Linear Regression. Notice there are a lot of different types of regressions here. Most of these are advanced techniques that are going to be used in very specific situations. Most of the time, for anything we're interested in looking at, we're looking for linear relationships. So once again, we're going to be actually looking at variables, but you notice it's a little more complex. On the left-hand side is the same list of variables. So this is where we'd click on our variables. However, regression requires us to actually predict what we're actually trying to quote unquote predict. In other words, we need an actual dependent variable, an outcome variable. In this case, I've selected an alpha of 0.81. So again, I've simply named my variable based on how reliable it was. Its internal consistency, it's Cronbach's alpha. However, I've also made a note that this is heterosexism short form. So that's going to be my outcome. Then my independent variables. And again, this is a simple regression, so I'm just going to be looking at heterosexism, another measure that's the long form. So basically, notice the long form also has an alpha of 0.96. So that's the one we were looking at last time. So now I'm actually asking, is there a relationship between a longer form of heterosexism or sexism and a shorter form, which is not quite as reliable? Now again, this is where regression also can become more complex. We can only bring one variable over as the outcome or the final variable that we're looking for the relationship in. But if we wanted to do something beyond a simple regression, we could bring over multiple predictors, independent variables. Again, you'll notice there's a method box right under that box where we put the independent variables. We're going to simply use the default of enter. And again, if you're in a more advanced statistics class, there are different methods that vary in how we're using regression. However, they only matter if we're looking at more than one independent variable. Once again, we're going to click statistics once we have our two variables over. We're going to again click descriptive so that we actually get the descriptive data as well. By the way, you can actually calculate descriptive data separately. This just allows us to have it all in one set. We're going to make sure that estimates are clicked, and other than that, we're really not doing anything here, and we're going to hit continue. Once we've done that, we're going to hit OK, and we're going to see what the results actually look like. So you'll notice we're getting more information here. We actually have 4 boxes compared to the correlation. We've still got the descriptive statistics, so we're getting the means and the standard deviations. In this case, we had 80 people take both versions of the test. We then actually have the model summary. Now, the reason it's a model summary here is, again, this particular technique is capable of looking at a much more complex model. But in this case, we're just looking at a simple bivariate correlation, but using regression. So notice R squared is actually calculated for us. So we have R squared. The adjusted R squared is generally going to be the same in this case. Adjusted R squared is again used when we have multiple predictors. We also have the standard error of the estimate calculated for us as well. So where we're actually getting R squared from is the model summary. This is the total variance that the model actually indicates. Where we're going to get degrees of freedom from is actually the ANOVA table. And again, for the purposes of simple regression, we're simply just getting some information from these tables. The further interpretation of these tables is more about how we'd be looking at a more complex multiple regression. And finally, we're going to get our actual value from the coefficients table. This is where we're actually going to be getting some information as far as the actual test statistic, which in this case is beta. And that's actually represented here. So our beta is actually negative 0.764. The t-test is actually our statistical test, and it is significant. So there is a significant relationship. We also get some information about prediction, which we're not going to go into in great detail here. But again, if we were trying to predict something, and if you're in a class using regression for prediction, this is where you're going to get your prediction information. It's the unstandardized coefficient, the B weight and the y-intercept. What y-intercept represents is what would be the score on your outcome variable if your predictor variable was 0. And what the B weight represents is how much increase or decrease that you get in your outcome variable for every 1 unit increase in your predictor variables or variables, depending. Again, in this case, simple regression, we only have one predictor. So how we would report this one is we'd report the B weight. It gives information on prediction. Again, the B in this case is capitalized and italicized. It's negative 1.18. We'd give the beta, negative 0.74. We'd give the t, and this is where we give that degrees of freedom, 78. We'd give the value of t, 10.45 negative, and finally the p-value, in this case less than 0.001. Notice that the significance listed is actually 0.000. We never report significance of 0. There's always a chance we're wrong. So if it's 0 or a number smaller than 0.001, we simply just put in p is less than 0.001. And finally, we give the r squared, the effect size, in this case 0.58. So basically 58% of the variance between these two predictors are explained by each other. So there is a pretty strong relationship between these two predictors. Now we're going to talk about how to calculate a scatter plot. So I've been showing scatter plots within the actual lectures we've talked about. Let's talk about how we actually create a scatter plot using SPSS. So in this case, again, we're going to have our data set. For scatter plots, just like correlations, they should be continuous data. So they should be numerical, sequential, and the numbers should represent approximately equal distances. So we're going to go to Graphs, Legacy Dialog, Scatter Plot, or Dot. We're going to select that. And basically now we're going to click a simple scatter plot, and we're going to click Define. Define is where we're actually going to be saying what the variable is. So again, we have a y-axis and an x-axis. So we're going to grab our variables from the left side screen. We're going to click on it. We're going to click the arrow to the y-axis. We're going to click on a second variable. We're going to click on it to the x-axis. And then we're going to click OK. So we're basically just telling it what two variables we want to look at a scatter plot of. We're now going to actually see the scatter plot, and each one of these dots represents one person's individual score. So again, this is a scatter plot of that data we were already talking about, where we are looking at the long form versus the short form of a sexism scale, with again this negative relationship. Now the reason it's a negative relationship actually is that the long form and the short form actually are scored in different directions. So high scores on one represent low scores on the other. So we actually would expect a negative relationship in this case. That's what we're looking for. Once it's actually there, we have the graph presented. We can double click on the actual field of the scatter plot, and that's going to basically bring us to this screen. We can go ahead and click Add a line of best fit, and we want to do that. It basically gives us an illustration of what kind of slope we're looking at, and then we're going to click Closed. And that's going to give us this scatter plot with the line of best fit. The line of best fit is how would you draw a straight line through the data points, minimizing the distance between each data point. It basically represents what kind of relationship. If it slopes downward, it's negative. If it slopes upward, it's positive. And the sharper the angle from corner to corner, the stronger the relationship. And the more flat the line, the weaker the relationship. So if this was no relationship, we'd probably see a straight line going along the horizon line. In this case, we know the relationship's fairly strong. So hopefully that gives you a good idea of how to do three things in SPSS: how we run correlations, simple regressions, how we report them, and how we create a scatter plot as a visual representation of what either that regression or that correlation is reflecting.